the pointer? This?
Yeah.
This red. Thank you. So, first of all, I'd like to thank the organisers for the opportunity to give a talk in this wonderful conference. I'll be talking about local wave functions in F-theory, some work I did earlier this year, and also some work I did before with Pablo Camara and Emilian Dudas. So let me begin with two general motivations for local models generally in string theory, because I think it's important to think about this. So string theory, as it currently stands, lacks a top-down vacuum selection principle. And this is a big problem for string phenomenology, of course. It's a problem not only because we don't know which of all the models that we can find is the correct one, but it's a bigger problem because we don't actually even know what the landscape is. The landscape is most likely not comprised of type 2b Calabi-Yau compactifications fully. That could just be a small part of it. It could be huge. It could be non-commutative, non-geometric spaces, whatever. We don't know what they are. So an important aspect to keep in mind, I think, always when doing string phenomenology is the sensitivity of the low energy observables or predictions of the theory to the choice of vacuum, which is essentially an assumption. We have no direct probes of this. And the important thing is that typically the more localized an interaction is, the less sensitive it is to the full vacuum that we have chosen to our assumptions. And therefore the more general the analysis is. So this is, I think, a strong motivation for studying things locally. All these assumptions that we always have to put in, even the fact that it's Calabi-Yau, might not be Calabi-Yau, who knows, all these things, we can do things more generally by looking at localized interactions. So that's the first important motivation. There's another important motivation, I think, and that is that calculating observables in string theory is hard. It's really hard. And actually calculating them, not approximating them. So typically you would find that in many models there are uncalculated order 1 factors, and typically the phenomenology can change a lot if this order 1 factor is order 10 or order 100, especially if we want to be giving LHC predictions, to 2-3 GeV or something like this. Then well, we have to know what these factors are, and they can easily be order 100. I mean, just because by symmetry a factor is not small, it can be that, as I will show. So it's important to try and calculate things, but it's really hard. And many calculations simplify considerably in the local approximation. And such an approximation is a particularly good one for particle physics operator coefficients. And that's because essentially in all string theories these are localized to some extent. And so this is another strong motivation for local models, and that is that we can actually calculate things, and we cannot calculate things fully without assuming all these unknown factors. And this has been typically used, as we just had a talk, to study Yukawa couplings in F-theory. These are localized, and you can actually try to calculate what the Yukawa couplings are. Okay, so given these two important motivations for local models, which I think really strike at the heart of the two deepest problems string phenomenology faces, that is calculability and generality, I think it's interesting to think about how far can we push this. And in some sense, the ultimate manifestation of a locality in F-theory and also in heterotic, I think, is the point of E8. Actually, surprisingly, we've had this mentioned many times already in the conference. So roughly speaking, it's the idea that you have in F-theory, some GUT7 brane with some, say, SU5 gauge group on it, and on it, the gauge group enhances over curves to some higher group. These are so-called matter curves. And where these curves intersect, the gauge group enhances even more, and there is an interaction, so an operator associated to this point. And it may be that the gauge group enhances all the way to E8. That's essentially the most it can enhance at the point. And then you have many, many different matter curves intersecting at that point. And if such a point of E8 exists, or even a small deformation of it, in the sense that you've not resolved it too far away compared to the string scale, so you have some effective theory based on this point of E8, then there is a very rich local theory around it, which allows us to study many phenomenological features explicitly and generally. So by rich local theory, I mean within this matter curves here, we have enough particles to account for all the standard model and many, many of its extensions, neutrinos, Yukawa couplings, all these things all fit inside this point of E8, and they will all be interacting at exactly the same point. So that is a very rich theory. We can have gauge mediating sectors, all kinds of things fit inside this point of V8. And when I say features explicitly and generally, I mean explicitly as in we can actually calculate couplings. We can really calculate them, not just the holomorphic part, the physical part, the normalized couplings, the things that we observe in experiments. And generally, well, because all I'm going to assume in this theory is that there is a point of V8. That's it. I'm not going to assume anything about if there's a Calabi-Yau completion or what the fluxes are, what the cosmological constant is, or any of these things. It will not affect the local theory. And that's the really, I think, a strong point, that we can study this without making big assumptions. We can calculate things, and it's a very rich theory. And in fact, it's such a rich theory that I think we've only just started thinking about what the local theory around the point of V8 is. And in this talk, I'll just report about some very initial explorations of the idea of what such a local theory is, what are the key concepts that I believe the key concepts in thinking about such a local theory, and what are the kind of operators that we can calculate in this theory, what are the kind of questions we can answer. So let me just begin about what is the actual tools we will use. So we want to describe the 7-brane around this point of V8. So our current only description we have, the best description we have, is in terms of the IR limit, in terms of some canonical 8-dimensional twisted super-Yang-Mills theory. And this theory has a gauge field in it and a Higgs field. And what we do is we give a background, a spatially varying Higgs background, such that this Higgs breaks the E8 gauge group to SU5 generically, but it vanishes on loci curves where the gauge group enhances, and these are the so-called matter curves. Apart from that, we also have to turn on at least a background flux, at least to generate chirality. So we need a chiral sector. So these are like the minimal ingredients we need. In these backgrounds, the matter fields will arise as fluctuations of the 8-dimensional fields. So these are the 8-dimensional fields, like there's a gauge field in the Higgs, and we take the gauge field with an internal index. So this is like a scalar, if you like. This will give us a chiral multiplet, n equals 1 4-dimensional chiral multiplet. The same thing from the Higgs. And we can also take the gauge field with an external index, will give us a 4-dimensional vector multiplet. So this is how the matter of the standard model arises in this theory. And each one of these multiplets will come from an 8-dimensional field. So it will have some internal profile along the internal directions. That is its wave function. And if we want to calculate some coupling in this theory, well, this comes from an 8D field theory coupling. It will just involve the coupling of the 4D fields. And the coefficient of this coupling will not be nothing but the overlap of the internal wave function of these fields. So this is how we can actually calculate these coefficients. Not like up to order 1 factors, we just calculate what they are. We just calculate these wave functions, normalize them, calculate their integral, and that tells us what the answer is. Schematically, the wave functions look like this in this background of flux and Higgs. Well, there is an exponential localization onto the loci where the Higgs field vanishes. That is the localization onto the matter curves. And another thing is that within the matter curve itself, there is localization due to the flux. So this is important. The wave function, if it's chiral, it will not be spread out over the matter curve uniformly. You can tell us just from supersymmetry, because anyway. The exponential localization onto the matter curves implies that it is possible to consider studying a point of V8 just on a local patch, because everything's going to be exponentially localized into the curves, and all these curves are going to interact at this point. So then any overlap calculation between these wave functions will be strongly localized at the point of V8. And so we can think about what kind of local backgrounds should we have. Well, you can just think about the most general background you can have at leading order in Taylor expansion around this point. So that's the most general thing you can do. This is the most general thing you can do. You just take a leading order in the coordinates, Z1 and Z2 on the gut surface for the Higgs. Here mk is some mass scale, the cutoff scale of your theory, which is like some kind of string scale. And these are local geometric scales, r parallel and r perpendicular. They are factors in the metric. You can think of it if, in terms of torus, let's say, then r parallel will be this length scale associated with s gut, and r perpendicular will be this length scale associated normal to f gut. But here they're just local things around the point of V8. And these are gauge generator indices. So typically when we study Yukawas, we take this to be inside U3 or SO12 or something. But this runs more generally, and in that case, this will sit inside the full E8, inside the point of V8. Same thing for the gauge field. This is the most general background you can take. Here, these M's are like the fluxes, if you like. It's linear, and there's a gauge generator index. And you take these backgrounds, you put them into the Dirac equation of this twisted Yang-Mills theory. It looks like this, where these are sort of Dirac operators along different directions. And I just put it up like, and you solve this to be 0, and that tells you what the massless wave functions are. You then calculate the integral of their overlaps, and tells you what the coefficient, the coupling between the massless modes are. This is the Dirac operators are not put it explicitly, but the only thing to note is that you can write this equation as acting on a vector where these fields, these are fermions coming from the gauge field, from the Higgs, or from the external legs of the gauge field to the gaugino. They all sit inside this vector very naturally and form an n equals 4 multiplet. Okay, so you can solve for my general fractions. You don't need to pay any attention to this. There's only two things I want you to get from this. One is that they have been solved for the most general local linear background. You can just solve for the wave function, but it's complicated. You know, these p's are given in terms of these p's, and these psi's are given in terms of this psi's, and these lambdas are given in terms of this lambdas, but it can be solved for. And the other thing is to note is that they're not just some very simple thing. There's many factors, and these factors get raised to higher powers. So it's very, very easy to start off with order 1 coefficients and get order 100 numbers out of it. So yeah, that's the other thing I wanted to point out. So, okay, so now I'm going to point out what I think are two important concepts in thinking about a model around the point of E8. And the first one is to do with the wave function profiles, not the localization onto the matter curves, but along the matter curves. And the relation of this to a local notion of chirality, and why I think this is important. So to understand this better, it's always good to have an example in mind. A kind of global example in the sense of, let's solve the wave function over a full matter curve. So let's take an example matter curve to be a P1, let's say. And the wave function is on a P1 in the background of flux. So I turn on some flux, which integrates to this M. So we should have M chiral modes on this P1. Actually, the wave functions were solved here in this paper, and they look like this. And we can see chirality generated from this flux directly in the wave functions. It manifests itself in the unitary frame, which is what this is, by the normalizability of the wave function. So, for example, if m is positive, then you see that these wave functions here, phi pluses, they are not normalizable. They diverge as z goes to infinity, and therefore we should throw all these solutions out. So we just end up with 1/2 of the solutions. So this has generated chirality for us. So chirality manifests itself in the unitary frame by the normalizability of the wave functions. In fact, you can see that if you say turn on 10 of these, then here in this arbitrary polynomial anti-holomorphic prefactor, you may take z to be 1, z squared, z cubed, and so on, up to, let's say, z to the 5 or something, when this becomes, again, non-normalizable. So it generates for you m solutions of 1 chirality, exactly what this chirality formula tells us. So you can just count chirality by looking at the normalizability of wave functions. And that's what the wave functions look like, essentially, always. If you have m of these, let's say you have 4 of these, you have 4 normalizable wave functions, and they just look like Gaussian peaks. And the key point is that they all have one peak, and this peak is along different positions along the matter curve. So why is that important? Why I think that's important? Because now we're interested in the patch inside the curve. This is where the point is, where the point of E8 is, where it intersects a different curve. And in that case, there are two types of wave functions we should think about. There's one case where the patch is such that the wave function does not have a peak in this patch. It does not have a peak around the point of E8. I would call this then a global mode. And the other one is when the wave function does have a peak. It has a turning point at the patch around the point of E8. And I would call that a local mode. The type of mode that we have is not fixed by the local theory. Whether theory is local, whether mode is local, wave function is local or global is not fixed local theory, and that is because the local theory has isometries associated to it that are, if you like, the remnants of Wilson lines, Tirode Wilson lines, and it means that you can always do an arbitrary transformation of coordinates along the matter curve, and the equations stay the same, and all that happens is that wave functions transform by a factor, which is just the holomorphic factor, which is part of the arbitrary holomorphic prefactor you have in wave functions. So by an appropriate choice of the arbitrary holomorphic prefactor, you can always move the peak of the wave function as you like along the matter curve to wherever you want in the local theory. Whether mode is local or global is fixed by the boundary conditions in the full theory and by orthonormality of the wave functions, just like any set of wave function solutions. So we cannot tell locally where the peak of the wave function should be. But whether a mode is local or global is constrained by phenomenology. So although we cannot fix this from the top down, we can constrain it phenomenologically, and that is because if the wave function peak, if it's a global mode, the wave function peak is away from the point of V8, then any operators that are associated to this mode will be suppressed because the overlap with this wave function will be small. So this tells us that, for example, third generation and the Higgs, so Tokugawa is order 1, so all the fields that are involved in the Tokugawa better have a peak in the wave function near the Yukawa point. Otherwise, the Tokugawa will be small. That's just some of these. So, for example, we can tell phenomenologically some of these modes better be local. They better have a peak. Actually, there's an additional motivation for the point of V8 phenomenological. We've had Kimon mention the fact that the CKA matrix tells you that the two Yukawa should be near each other. There is a similar one when you start thinking about the peaks of the wave functions inside the matter curve. And that is, for example, that is because the same 10 curve, the same 10 matter appears in the bottom Yukawa and in the top Yukawa. But this 10 matter will have some peak somewhere. But if you say in large town beta, you have a large bottom Yukawa and a large top Yukawa, then this peak better be close to each other and both be sitting near to this peak. Otherwise, if one Yukawa is far away from this peak, then it's going to be very, very small. So the fact that, let's say, if you're in large town beta, both the bottom Yukawa and the top Yukawa are big, tells you that they both better be sitting near the point where this wave function peaks, and so they better be close to each other. Again, coming together towards the point of V8. Anyway, why am I so interested in the difference between these local modes and the peaks of these wave functions at the point of interaction? Because for local modes, there is a constraint. The chirality of the local mode is related to the local form of the flux. So chirality is typically something we think of as something global. We have to write flux, integrated, and something like this. But actually, if the wave function has a turning point, then the local form of the flux determines the chirality of that wave function. This is like related to the ideas of Morse theory, if you like, where you can look at functions on a space, and you can calculate the homology by the turning points of the functions. Exactly the same thing's happening here. And the point is that if you have a turning point in a local patch, then the chirality of that mode is given by this formula explicitly, where this is, remember, the leading order local flux and local Higgs. Why is this important? It's important because if you have a point of V8, then you have many states, and you want a particular chirality for, let's say, the top generation, the 5s, the 10s, the Higgses, whatever you want, but you have very few fluxes because you are just looking at a local point. You're just in flat space. You don't have any cycles you can turn the fluxes on. You don't have the landscape of fluxes. You have hardly any fluxes, but you have many states. So in fact, if you start to think of realizing realistic models around a point of V8, where the wave functions are peaked at a point of V8, which you need to phenomenologically, then you have very non-trivial constraints to satisfy. And this is, in some sense, local spectrum model building. So this is like model building on a point you have to do. And it's non-trivial to do this. In fact, I think like one of the things I looked for is modes where all the matter is generations distributed in different curves, and they're all peaking at the point of V8, and I could not find such a model, for example. But there are other constraints. It's non-trivial to build a model based on a point of V8 where the wave functions peak there. Okay, what is another important concept that I think is important when we think about this, which is really important from the point of V8, is the point of massive modes. So the thing is that in a local theory, you can also start studying massive modes. These are massive excitations spatially. And all you do is you just have your Super-Yang-Mills, you have some Dirac operators in this theory, and you just calculate the commutation relations, and then from that you generate raising operators, and then you start exciting your zero-mode wave functions. So you can write down a massive mode like this. It has 3 integers labeled in it. It's just a number of times that the raising operators have acted on the massless mode wave function. And this P is this n equals 4 index. It's sitting inside this vector which runs over from 1 to 4. Yeah, like massless modes, they sit inside this n equals 4. You see that, yeah, you can just generate along the n equals 4 towers. There are 2 types of massive modes. There are Landau levels. They arise in the presence of flux and are n equals 1-like, so they're chiral-like. So for example, this is a spectrum of one level, if you like, of Landau levels. So these lambdas are some functions of the flux. They're non-zero. So this is the mass. So you see there's just 1, 0. So you have a chiral mode. And all these heavy modes are what I call Landau levels. These are the analogs of winding modes, actually. And the other types of modes are KK modes. And they are n equals 2-like. They're non-chiral. So they would correspond to the case when you turn the flux such that lambda 3 goes to 0 here, and then you start seeing that everything pairs up. So you see 0, 0, 1, 1, this lambda 3, I don't know, yeah, lambda 2, and so on. Yeah. Okay. I don't know what this your partner this is. Okay, yeah, I know what it is. The sum of the lambdas goes to 0. So when he says lambda 3 to 0, lambda 2 is equal to minus lambda 1. So then these two match up. So the spectrum pairs up into n equals 2 spectrum. And that's a KK spectrum. There's a difference between a lambda level spectrum, which is chiral. Okay, so the coupling of massive modes to massless modes is just done the same as the coupling of massless modes to each other. You calculate the wave function of the massive mode, you integrate its overlap with the massless modes, and it tells you how these couple to massless modes. This will be very important for phenomenology, as I'll mention out later. This particular coupling, it features very heavily in gut theories. But another thing is that massive modes couple to each other. And why is that important? That's important because you want to integrate them out to generate higher dimension operators, which are constrained by phenomenology. So you have to know which modes couple to each other, and the coupling is non-trivial. They don't just all couple to each other. They couple to each other through the 8-dimensional kinetic term. And the point is that this derivative operator acts like a raising-lowering operator, so they couple different sectors to each other in a complicated way. So this is an example of a sector that couples. So this is the four-dimensional massive mode, if you like. You see that it couples different n equals 4 sectors to each other. This is 0, 2, 3, 1. And it couples different excitations to each other in a very particular way. But the point is you can calculate it. You can calculate which massive modes couple to each other. So once you have this, let me give just a brief example of the kind of things you can hope to calculate around a theory at point of V8. The kind of questions we would like to answer that have featured heavily in F-theory phenomenology all this time. But we've not been able to calculate the actual factors that matter. So here you can calculate them. So let me just give an example. First of all, you have to find a model around a point of E8. This is non-trivial. So you think this is E8. So our model is labeled by these 4 extra U1s. So if you like, there's 5 indices with a tracer set constraint. So first thing you need to do is find the flux and Higgses that are compatible with the chirality of the MSSM spectrum having a peak around this point of E8. That's a non-trivial exercise, but you can do it. So this is one set that you find. This is this model building aspect that I was talking about. And if you take this, then this implies, according to the chirality formula that I gave, that the following modes can be taken as local. So it can have a peak at the point of E8, the wave function. So there you see you can put in some heavy generations. These are localized there. And these are the 5s. These are the 10s. These are the 5s. And you see I picked the hypercharged flux so that you have the Higgs doublets, but the triplets are non-chiral. So the triplets can be KK modes. They can be have isometry along the matter curve, and they can be lifted. Whether they're lifted or not, you cannot tell in the local theory. This is set by the boundary conditions. It's whether your H0 is 0 or not on the matter curve. But it's compatible with the triplets being heavy, whereas other choices here would not be compatible. So it's non-trivial. OK. So let me give an example kind of thing that you can calculate, something that featured heavily in F-theory phenomenology, which is dimension 5 proton decay. So the points, dimension 5 proton decay, and in particular in the presence of a U1 Peccei-Quinn. So dimension 5 proton decay, remember it happens because the heavy triplets, after double triplet splitting, couple to the fields in the Yukawa-like couplings. And then when you integrate these triplets out, you generate some high dimension operator, QQQL, which leads to proton decay. So here I'm going to look at an even more complicated case, which is when the U1 charges of the fields are such that there is a U1 that forbids this dimension 5 proton decay. So you see these triplets don't have a direct coupling to each other, but they only couple, these are heavy triplets, through an extra singlet mode. And then when you integrate them out, you find this operator. So it's a singlet under the standard models, but it has charges of these U1s to make this coupling natural. And you find this, this is a dimension 5 operator. This is constrained by experiment, right? It's very strongly constrained by experiment, proton decay. And the point is that now we can actually calculate what these numbers are. So to calculate, OK, lots of time. So to calculate this number, you have to calculate an overlap of a massive mode wave function of a triplet in this background of Higgses and fluxes that I had in this more general solution of 2 massless modes, these things. But the point is you can just calculate what these things are. You don't have to estimate, you don't have to do anything, you just calculate them. And you can calculate all these things here. You even know the masses of these massive modes. These are massive KK modes. And you're particularly interested in the relation of this to another operator, which is of this singlet to some pair of exotics that you may or may not have, but you typically find once you look at a global model. And this has some particular coupling, which again you can calculate. Why are you interested in this? Well, because to kill proton decay, to make the exotics, to decouple the exotics, you typically, this is a typical problem that comes up in F-theory, you want to make these exotics very heavy to retain gauge coupling unification, so you want to give this X singlet a big VEV, but on the other hand, you want to not allow big proton decay, so you want this X to have a small VEV so that you don't have proton decay. And this competition between the two is quite subtle actually, and it relies on order 1 factors, order 10 factors, order 100 factors to actually be able to determine what value, what VEV this singlet can have. You need to know order 1, order 10, order 100 factors to actually tell this. So you can do this calculation. You can calculate what all these parameters are, and in particular you can calculate the ratio of the two, because then you're not sensitive to the normalization of the wave function of the singlet, which is something subtle to do with these local models. But okay, so we calculated them, we know the wave functions, we know the integrals, we just overlap them and so forth. And you find this result here. And you find this actually very small number here. And that's quite nice in a way, because it tells you that this proton decay operator is quite a lot suppressed compared to this one that raises the exotic's mass. So you can take X to be at the string scale, if you like, decouple the exotics completely, but this would still be very strongly suppressed. Just because these couplings are smaller, they're not order 1. So when we study these things, we always assume these are order 1, we can't calculate them, and we just play with the singlet VEV. But if you calculate them, you find new numbers, and you find that it can be very small, in fact. So this is the kind of answers we can answer, kind of questions we can answer in a local model that we would not be able to do generally. Now, I'm not saying this is the model of the universe, or this is a problem way to solve proton decay. I'm just saying this is an example of the kind of things we can calculate and the kind of things that can happen. You can find numbers that are not order 1, they're order 10 to the minus 3, 10 to the minus 4 more than what you thought. Okay, so that's the thing. So let me just raise 2 issues, or maybe 1, depends on what the time is, that are general challenges to meet, I think, already at this level. In this model, I find small Yukawa couplings. In fact, the product of the two, the top and bottom, is 10 to the minus 5. That's a bit too small than what we want. Okay, this is just a comment that even with these Yukawa couplings, you still find more suppression of proton decay than you would from naive field theory analysis. Anyway, and the general issue is the following. It is actually quite tricky to find order 1 couplings from wave functions overlap. And the reason is that there are 2 localization effects on the wave functions. There's the Higgs localization onto the matter curves, and there's the flux localization inside the matter curve. And the 2 effects are actually different strengths. And this is related to the F-theory idea. For order 1 complex structure, it's possible to make the flux one more localized with more complicated complex structures, but in this theory, they're different strengths. And this means that if you look at the wave functions, along the matter curve, they are like this. They are peaked, but quite broad. Whilst if you overlap this with another wave function, the matter curve going into the board, it will be very strongly localized by the Higgs. And then the point is that the overlap integral only receives contribution from this patch, but the normalization integral receives a contribution from all of this. And so when you correctly normalize the wave function, you nearly always find that the coupling, when calculated, the physical coupling, it's actually small. And this is the basic reason why. So this is something that needs to be overcome, I think. It's essentially it leads to the effective suppression by the modular weight, but I won't get into that. And then finally, let me mention another general issue, and that is that the effective theory that we even started working with, the 8-dimensional Super-Yang-Mills theory, is generally not compatible with the so-called decoupling limit, where we take the Planck scale to infinity. And the reason for this is an important point in the sense that if we want to work in a local model, decouple the Planck scale to infinity, and then the actual theory we have for this local model breaks down, generally. And the reason is the following. In this theory, we have to keep high derivative operators under control. We're just dealing with canonical n equals 8-dimensional Super-Yang-Mills. And there are 2 types of high derivative terms. One associated to the flux, so you want to keep flux density dilute, essentially. And you want to keep also the Higgs density dilute. You want to keep derivatives of the Higgs small. if you like, the two are dual to each other in the sense that the Higgs is like the flux in the 10D theory, the T dual to it. So you want to keep the Higgs dilute and the flux dilute. But the point is that the Higgs measures the scale normal to the brane, and so and this scale is related to the strength of the gravity. So if you want to take m Planck to infinity, this p is some power depending on the geometry. So like for a torus it's 2, I think, and for a shrinkable cycle it's a third or something. But it's positive. It's a positive power. It always is because of gravity. Now you send this to infinity, you also start sending the Higgs gradient to infinity, and this gets ruined. And there's multiple ways to think about this issue. One way to think about the T dual, if you like, where this Higgs turns into flux, and then sending this direction to infinity is like sending a cycle to be very small, and you get very large flux densities. And this is breaking. So this does not affect the holomorphic sector of your theory, but it ruins your Kähler potential. Another way to think about it geometrically, let's say if you think about a torus, then if this is our brane, this is another brane intersecting it, and this position of this brane is nothing but the Higgs wave. Then you start taking this size to infinity, you want to take decouple gravity, but this is quantized, because this goes round in a torus. So then you start seeing that this angle starts to get bigger and bigger and bigger, and you get large intersection angles. And that is when your theory breaks down. That is the same as this. You get high derivative terms as large intersection angles. So this is just a torus, but the basic concept is the same. The Higgs always measures the normal direction to the brane, and this number here is always quantized. It's a Higgs bundle, and it's quantized. And the torus is quantized because you have to go around the torus, but it's always quantized. It's a holomorphic bundle. So this is another challenge, I think, to meet, in that generally the effective theory is valid in this regime, but this regime is not the same regime that you naturally want to be in if you want gravity to be much larger than the other scale. There are ways around this, like for example, this Higgs measures the distance not to the bulk, but to the other brane. So if the branes are not bulk branes, that the flavor branes, but also local branes, then you can avoid this issue. But there are ways to avoid it, but that's generally should to be aware of, I think. Okay, so to summarize, local models around enhanced symmetries like Yukawa's, and the most complete model being that around the point of E8, are an interesting set of constructions, I think, in F-theory and probably in heterotic as well. They offer potentially highly calculable, general and predictive theories, which have very few input parameters. There's no millions of cycles to turn fluxes on, very few input parameters, and they output a lot of calculable particle physics operators, which are the things that are most constrained by experiment. We have dozens of constraints on particle physics operators. Yukawas, mixings, whatever, lots of constraints, few input parameters. Toy models show that many coefficients that by symmetries alone would be order 1, that we quite often would take things to be order 1, can actually be much smaller and larger than order 1. And this may shed new light on some long-standing phenomenological issues like proton decay and like many things. Now, importantly, this is just starting a study, I think, of these local models, especially around the point of E8. There's still a long way to go for realistic models. For example, you need to include monodromies or T-branes, same thing. You need to maybe include non-commutative deformations and all these things. And I think once you do all these things, the future difficulties are much more likely related to differential rather than algebraic geometry. Because you start finding equations that you can all solve by hand, and you start having to solve them numerically. And if in the future we go along this idea with, like say, a local model around the point of E8, we start to model build around that, looking more and more realistic models, then I think the tools that we currently have in algebraic geometry will not be so much useful, but instead we'll have to start learning to do differential geometry, numerical solutions, and so on and so on. But that's just the far future idea. That's it.
Questions? So there was this motivation for having this point of E8. One motivation was that have up curves and down curves intersect at the same point so they can have small CKM angles. Did you suggest, or did you say that that's also related to maybe having large tangent beta?
Yeah, in the following sense, that if you imagine this is the 10 curve, and you have a 5 bar 10, and you have a 5, 10, 10, okay? And let's say this is Yukawa B, Yukawa top. Then let's say I put Yukawa top here. Then I know this must be order 1. So I know that this, because this reference is chiral, it means it has a peak somewhere. Otherwise it would be n equals 2 if it's spread out. So I know this peak better be here, because the peak of these three things overlap to be 1. So I know this wave function better look like that. But now, if I take tangent beta to be 50, this guy also better be big. Right? This by 0.1 or something like this for tangent equals 50. So it tells me that this coupling better also be here at the peak. Otherwise, if it was here, it would also be small. So then, again, I'm bringing the two cows together, and so I'm reaching the point of V8. But this is not related to the model of flavor that you have, the CKM matrix or something like this. In fact, this is essentially the distance between them is directly related to tangent beta. 1 over tangent beta, if you like.
Timo?
This observation that some factors which maybe would be order 1 then turn out to be totally different. Does this depend on the particular type of configuration or on other data like the particular realization? So could you play with it? Could you dial this, or is this set once and for all once you specify your E8 times you want to do 4 model or whatever?
I think it would depend on your local fluxes and things like this. I don't know how much it can vary due to your local fluxes or not. I mean, I studied this. First of all, it's quite constraining to even find a flux so compatible with this chirality. And then once you find them, you want to keep them dilute and something like this. And once I did that, I found these very small numbers. I mean, I did play around with fluxes, and you can start getting different numbers if you take different fluxes. But it's not a huge amount. Because of this general problem that I said, couplings are typically small in this theory. There's only so much you can do. For example, I couldn't play around with the fluxes to suddenly make the Topikawa 1. It was always 10 to the minus 2 or something like this. And that's because of this different localization effects. I think this is known from like intersecting brane models in extra dimensions, in the sense that you want to localize things along the curve as well as with the curve so that your overlap integrals are 1.
More questions, Fernando?
The issue about the setting the end plan to infinity, that is, can be complicated because you have the 2 different scales. Will that be used as a constraint in a sense for model building eventually?
Well, I don't think it affects. Well, it's not calculable to me how you can that can affect an actual observable. It's more that the theory would break down in this theory. So you would just the Keller potential would get higher derivative corrections, and then you don't know how to normalize your wave functions. So
you have to find ways out on the way out, maybe.
So there's 2 ways out that I know of. One is that gravity is finite. So this R perpendicular actually is only about a factor of around 10 or something like this. If you have a local model, this P number I had, it's the smallest for a local model. So it's like motivation for local models. It's the biggest problem in a torus, let's say. If you have a local model, R perpendicular is just around 10 if you have gate couplings, and then the volume is 10 to the 6, right? But in here, in these models, you need it to be around 2 or 3 or something like this. So it's not such a big difference between the 2. But this, remember, the one that sets the scale of gravity is a global scale. And this here is a local scale. It's a scale to do with the metric around the point of V8. So all you need is some kind of inhomogeneity such that your space is a bit flatter, factor of 3 times flatter than the average curvature near this point of V8, so that your theory is well defined there. In fact, you can never define a theory on the full S-cut where this happens, because you have to come back to yourself. But if you're looking at a patch, all you need to be is in a particularly flat patch, and your theory is okay. And the other thing is that the Higgs, this is kind of scaling ideas, but the Higgs really measures the distance to another brane. And what I've assumed here is that the other brane, the flavor brane, goes into the bulk, so that it scales with the same R that scales gravity. But if it's not, it can just be a local brane. You can have 2 intersecting branes, and they both be local. In that case, even if you decouple gravity, the Higgs will still stay the same, because it's measuring the distance to a brane, not to the distance to the Calabi-Yau. So that's another configuration where you'd avoid this problem. But if you have a bulk brane, a flavor brane, which is in bulk, and you start pulling this guy away, your theory will break down on the 7 brane. That's the point I was trying to make.
Okay, I have a simple question. What about dimension 4 variant number violating operators in the E8?
Well, this is just done by the gauge group. So
how can you forbid? How you can get R parity or anything like that?
So this is not to do with the wave function overlaps. This you would forbid with the U1 symmetry. So then you have to look at what your spectrum is and whether the U1 symmetry forbids this operator or not.
So U1 symmetry.
I would say U1 symmetry. I don't think the wave functions can give you a 10 to the 16 suppression that you need for these things for dimension 4 point of the gate.
Okay, so we thank Eran again.